Alright, so we are jumping into Chapter 6 here. Chapter 6 talks about thermochemistry, and thermochemistry deals with the energy associated with chemical changes. We've discussed how chemistry is the science of change. That's sort of the name of our textbook, subtitle of our textbook. And so thermochemistry is the energy changes that are associated with those chemical changes. So first off, let's talk about energy and how energy applies to chemical reactions. First, there are lots of different types of energy. We have radiant energy, which for us is solar energy coming from the sun. It can be, radiant energy can be from any light source, but we generally think about it as being solar energy. Thermal energy, associated with the random motion of all things, all atoms, all molecules that are moving about randomly. That's thermal motion, thermal energy. And that's the energy that we really will focus a good bit on, because that's sort of the energy that we think of as something being hot. The hotter it is, the more thermal energy it has. Chemical energy is the energy that's stored within chemical bonds for a particular compound. And so between these two, thermal and chemical energy, that's where we'll find a lot of our discussions in this chapter. Nuclear energy takes it even further, so we're not talking about bonds anymore, but we're talking about within the nucleus of an atom, and there's a lot of energy there. Think about a nuclear bomb or something like that, a nuclear fuel. Last chapter, in chapter 5 with gases, we talked about the kinetic molecular theory and how the kinetic energy of gas molecules is related to their temperature. Now we're going to talk about potential energy. So we talk about thermal energy, sort of being like kinetic energy, the speed of a molecule depending on its temperature. Now we're going to talk about potential energy being connected to chemical energy. How much energy a particular compound can release depends on how much energy is stored within those chemical bonds. All right, and so the different types of energy changes that we see in chemical reactions. Two words that we'll throw around a lot are heat and temperature. And I just want us to make sure that we're on the same page with these two, because these two are not the same thing, right? When we talk about heat, we're talking about a transfer of energy that thermal energy between two components, two things, two objects. Our textbook uses the term bodies because it could be a body of water, a body of air, and those things may or may not, you may not think of those things as objects. And in order to have this transfer of energy, they must be at two different temperatures. Right? And which direction does the energy flow, the heat flow? Will it flow from cold to warm or warm to cold? Warm to cold, always, right? And so heat always flows warm to cold. Okay? Temperature, on the other hand, is sort of how we think about the thermal energy of a system. And so temperature is a measurement or a way to measure of thermal energy. Right? The thing that I really want to make clear here is that when we talk about heat and we're talking about this change in thermal energy, that change in heat does not necessarily mean anything about the change in temperature. And so temperature and thermal energy are not the same thing. Temperature is how we measure the thermal energy of an object or of a body. Right? The heat is the energy that's transferred between bodies. And so it gets a little confusing, but we need to keep these three terms separate. Heat, which is always a transfer. Thermal energy, which is the energy that an object has due to random motion. And the temperature, which is the way that you and I and scientists measure how much energy is there, right? So those three terms, we need to keep those separate. So, thermochemistry is the title of our chapter. And remember, thermochemistry is this study of thermal energy and how it changes. And so it must be the study of heat change during chemical reactions. I remember RXN, my abbreviation for reactions. When we talk about this change, whatever we are most interested in, that's going to be our system. And everything else is the surroundings, right? And so when we think about this thermochemistry and where this heat is going between, which objects, which bodies is this heat being transferred between, we have the system and then we have the surroundings. And so the system is the specific part of the universe that we're interested in. Right? And so there are three main ways that the system and the surroundings can interact. In flask A here, we have an open system. In an open system, you can see we have exchange of both heat, so heat can be exchanged between the system and the surroundings. That is, there is a change, a flow of thermal energy. But we also, they're using water vapor here, but we can also exchange mass. Right, so we have an exchange of mass, but we also have an exchange of energy. Okay? Think about just a beaker out on a bench top. In the next picture, in part B here, we call this a closed system. In a closed system, you can tell we've just put this stopper on, and so we have stopped the flow of mass. We've stopped the exchange of mass between the system and the surroundings. But what we haven't done is we haven't stopped this flow of heat, that exchange of thermal energy between the system and the surroundings. Think about a water bottle that you leave in your car on a winter's day, right? When you put it in there during the day, when it's sunny, it's fine. You come back early in the morning when it's still cold outside and that bottle has shriveled up a little bit. That's because the temperature of the water and the gas inside the bottle has changed and they have condensed. The volume has lowered. But because we couldn't exchange mass, we couldn't add more air in there to maintain the shape, the volume of that bottle. The bottle gets distorted a little bit. That's a closed system. This last type of system is called an isolated system. And so you see it still has the cork in it so that it cannot exchange anything with the surroundings, but now also it has this insulation all the way around it. And that insulation all the way around it keeps it from exchanging heat with the surroundings as well. And so we have neither the exchange of mass nor the exchange of heat. And again, that's an isolated system. Think about a thermos or a cooler or something like that. All right. And so if we're going to talk about energy change and the heat, the flow of energy between systems, we're going to have some terms that discuss that. And so the two terms that we're most going to use most often are endothermic and exothermic. In an exothermic process, right? Exo, outer, think about exits, right? In an exothermic process, we have energy leaving the system. And if it leaves the system, where does it go? Well, it's got to go to the surroundings. Remember, the surroundings are everything else. And so if it's exothermic, we have energy leaving the system. We think about this as giving off heat. Right? Usually that's accompanied by a decrease in temperature. If we have an endothermic system, or an endothermic process, rather, then, of course, that's going to be energy that goes into the system. These kind of endothermic reactions, or endothermic processes, absorb energy, or absorb heat. Okay? So exothermic, energy leaves the system, giving off heat to the surroundings. Endothermic, energy going into the system, absorbing heat from the surroundings. If we were to write this out, sketch this out as a schematic, this is an image from our textbook. We have on the left in part A, we're going from the hydrogen gas and oxygen gas to make water liquid. Going from a gas to a liquid is, generally speaking, lower in energy, and so that energy has to go somewhere. That's exothermic. All that excess energy is given off. Right? In the part B here, we're going from this mercury oxide solid to mercury liquid and oxygen gas. To break those chemical bonds, we have to add more energy in, and so they have to absorb energy from the surroundings. To think about a chemical bond and why we have to add energy in order to break a bond, think about it this way. If chemical bonds were higher in energy than the elements themselves, then everything would just exist as elements. We wouldn't have any chemical bonds because they're higher in energy. And remember, we talked about the fact that nature loves lowest energy things. We talked about that when we did the Aufbau principle, that building up rule. And so every time we have a chemical reaction where we form a new compound, those bonds that we form are absorbing energy. Those bonds that we form give off a certain amount of energy, and when we break those bonds, we have to put the same amount of energy in order to break those compounds apart into the elements. Enthalpy is a little bit different from energy. Let me go back a slide. Here on our y-axis, we have energy. We've talked about thermal energy and all that stuff. We're shifting a little bit from energy to enthalpy. Right? This is a new term for us. And enthalpy is the overall energy of a system with one caveat. And that caveat is that we are at constant pressure. And so enthalpy is given the symbol H. And so this enthalpy is the energy change in a system at constant pressure. So why constant pressure? Well, it turns out that most of the things we do in the lab are constant pressure situations. We're doing a reaction in a beaker, it's open to the pressure of the room. And so we deal with constant pressure worlds most of the time. And in this example, again, we're going from a solid to a liquid. So from a solid to a liquid, that's melting. Do we have to add energy to ice in order to make it become water? Or do we need to remove energy from ice to make it become water? Of course, we have to add energy. We have to heat it up. And so that's endothermic process. And the sign of delta H is positive. Right? Delta H, that change in enthalpy, is a positive value. That means that we are endothermic. Right? On the other hand, over here, we have methane and oxygen going to CO2 and water. What kind of reaction is that? A fuel plus oxygen makes CO2 and water? I hope you said combustion. Combustion, we know, gives off heat. You see that the sign of delta H here is negative, and so when delta H is negative, that's exothermic. That's giving off heat, giving off energy. Okay? Where these numbers come from, when we talk about delta H, we talk about it as the enthalpy of the products minus the enthalpy of the reactants. And so we'll come back to that later on in the chapter, but this thinking about things as endothermic and exothermic, I want you to have a pretty good grasp of here at the beginning. Okay? And so a few things to keep in mind as we move more into thermochemistry. First, when we talk about stoichiometric coefficients, what are those again? Those are in our balanced chemical equation, right? Our coefficient here and our coefficient here. They're both 1 in this case. But they refer to the moles of a substance, right? When we write delta H, it's almost always in units of kilojoules per mole. Right? We've seen joules before when we did our chapter 5 stuff. But joules are our SI unit for energy. And we're dealing with kilojoules, so that's 1,000 joules-ish per mole. Now that per mole is per mole as written. And so it's 6.01 kilojoules per 1 mole of solid water. Okay? The second thing to take into account is if we reverse this reaction, so instead of water as a solid going to water liquid, now we've got water liquid going to water solid. Well, instead of adding in 6.01 kilojoules per mole, now I've got to take out 6.01 kilojoules per mole. And so I change the sign of delta H. So delta H is now negative 6.01 kilojoules per mole. Right? So you reverse the reaction, you change the sign of delta H. Let's say that for some reason we're dealing with something and we need to have twice as much of a particular product or a particular reactant. Maybe we need to double the whole reaction. Right? And so if we change coefficients for a particular reaction, now we have 2 H2O solid going to 2 H2O liquid. Well, if it was 6.01 kilojoules for 1 mole, how many kilojoules must it be for 2 moles? Well, it's going to be 12.02 kilojoules per mole. Now, the thing to keep in mind here, and the thing that, going back up to this first bullet point, 12.02 kilojoules per mole. It's still 6.01 kilojoules for every 1 mole, but the way that enthalpy works is that it's kilojoules per mole as the equation is written. And so because now I have a 2 here, if I were to use this enthalpy as a conversion factor, it would be 12.02 kilojoules for every 2 moles of water. If I were to use it as a conversion factor here at the top, it'd be 6.01 kilojoules for every 1 mole of water. These are perfectly equivalent, 6 divided by 1 is 6. 12 divided by 2 is 6. The energy per mole doesn't change. It's just the way that we notate that when we write it out is that it's kilojoules per mole as written. We just have to take into account what those coefficients are. Another important note about dealing with thermochemistry and these reactions is that it takes energy to convert from one phase to another phase. From solid water to liquid water takes some energy. And so it is supremely important that we start, if you haven't been, or continue to write the phase conditions, the states for our reactants and products when we write chemical equations. Okay, solid to a liquid, this transition, 6 kilojoules per mole. But if I'm going from a liquid to a gas, that requires a lot more energy, 44 kilojoules per mole. All right, let's do a quick example and we'll be done with this video. We have this reaction here, 2 moles of SO2 plus a mole of oxygen give us 2 moles of SO3. We have a change in enthalpy of negative 198.2 kilojoules per mole. A couple things I want to point out before we even get started. Delta H is negative. Right? So is that endothermic or exothermic? If the energy of the system is going down, that means that the system is giving off energy, which makes it exothermic. The other thing to keep in mind, with this information, this kilojoules per mole, like I was just saying, we could write a few different conversion factors. I'm going to go ahead and write all 3 without even reading the rest of the question, because I want you to know what I mean when I say that it's per mole as written. For this reaction, 198.2 kilojoules are released. So negative 198.2 kilojoules of energy are released for every 2 moles of SO2. But it is also perfectly true that 198.2 kilojoules of energy are released for every 1 mole of oxygen. It is also true that negative 198.2 kilojoules of energy are exchanged for every 2 moles of SO3. And so we can write all 3 of these conversion factors, and the number of moles on the bottom is the same as that coefficient in the balanced reaction. Make sure you balance it. So we're going to calculate the heat evolved, so how much heat is given off, evolved like a gas, given off, when we have 87.9 grams of SO2 converted to SO3. So we start with the one that's not a conversion factor. 87.9 grams of SO2. We're going to use our molar mass here to go from grams to mole. 1 mole of SO2, 64.07 grams of SO2. My grams cancel. And so now I'm going to use the right conversion factor based on what I need to get rid of. I need to get rid of moles of SO2, so I'm going to use this first conversion factor, negative 198.2 kilojoules for every 2 moles of SO2. So now my moles of SO2 cancel, and I'm left with just kilojoules. I'm asked for heat. Heat is thermal energy, right? And so kilojoules is a good unit for heat. So we do some calculations, and we end up with 136 kilojoules of energy that are given off. Let's talk a little bit, just a second, about signs. The answer here, the heat for this reaction, is negative 136 kilojoules. If the question says how much heat is given off, we don't need that negative sign because negative amounts of heat weren't given off. That would mean heat was absorbed. And so it can get really tricky with wording. The answer that we should think about is 136 kilojoules of heat were evolved. Right? That means that 136 kilojoules of heat were given off to the surroundings. Okay? All right. When we come back, we'll talk about specific heat capacity and calorimetry.